Okay, so take a moment to write this down. This part here when where I wrote the main property of convolutions. And so let me read it for you and then illustrate it with examples. But again, remember what we discussed in the previous part of the lecture. This is the main motivation, right, for inventing this new operation called convolution. So whenever you have a convolution between two functions, again, not just a regular product, but this new operation, feel free if you want to distribute the Laplace operator and then have the regular multiplication between them. So L of the convolution of f and g, it's going to be the product of L of f of t and L of g of t. Or, as you know, the alternative notation, big F of s, which is L of f of t, big G of s, which is L of g of t. So you can have that option, and obviously you can use that in reverse. You could, when you take the inverse Laplace. So when we have the inverse Laplace of the regular product, not the convolution, but the regular product between two functions in S, you could distribute the inverse Laplace operator as long as you have the convolution between them. So the inverse Laplace of a product of two functions in S becomes the convolution of the inverse Laplace of each of these factors. So that means at this point you actually can write the Laplace transform or the inverse Laplace transform in multiple ways. So for example, when you take the inverse Laplace, for instance, so let's say you take the inverse Laplace of 1 over s squared. So on one hand, you know that the inverse Laplace of 1 over s squared is actually t. But by the same token, you could make the distribution of the inverse Laplace, because you have 1 over s times 1 over s, and you could say that this is the inverse of 1 over s convolution inverse of 1 over s. So what's the inverse of 1 over s? Well, from the table is 1, the constant function 1, and the other one is 1. So in other words, either you write t or 1 convolution 1, this is all the same thing. Now, which one would you prefer? If you don't have any reason why one way or another, it doesn't matter. Now, obviously, in this case, I would prefer t, because, I mean, what's the point of complicating my life with a convolution and then dealing with an integral when I can have an immediate formula for 1 over s squared? But you'll see later on that there are situations when you are much more efficient if you use the convolution. For now, let's just practice with this main property to understand how it works. Let's say from left to right. Let's say I take the Laplace operator of, let's see, I have an example here. T e to the 2t. There's a formula, by the way, in the table for this. So from the table, this is actually 1 over s minus 2 squared. From the table. Yeah, I was going to say something else about this. So let's take actually the inverse Laplace, because this is just a regular product. So the inverse Laplace, obviously, of 1 over s minus 2 squared equals t to the 2t, again from the same table. But again, this one now is a regular product of two functions, so you could write this via a convolution by distributing the inverse Laplace operator to 1 over s minus 2 and 1 over s minus 2. So this will be the inverse of 1 over s minus 2 convolution inverse of 1 over s minus 2. And now again from the table, this is equal to e to the 2t convolution e to the 2t. So if this, for example, would be the answer of an initial value problem, whether you write it as t to the 2t or convolution between e to the 2t and e to the 2t, this will be the same thing. One of them written in terms of a convolution, the other one just in terms of the regular multiplication. So once we do this, let's actually move on to how we actually solve a differential equation with convolution. So the next topic, how we solve a linear ODE with convolutions. So before we move on to how we solve a general linear ODE, we're going to do a specific linear ODE which have a specific right-hand side function. And it will make sense why we do that first immediately. Just be patient a little bit, but it will make sense once we move on to the general linear ODE why we actually do this. So I can actually anticipate a little bit. The reason we do that example first is because the solution will look in a very standard way, so to speak. So it will give you basically the idea of a nice recipe of solving any linear ODE. But again, it will be clear once we get to that generalization later, so to speak. So for now, let's focus on this example. So let's take this particular linear ODE with delta t, so the impulse function at time 0, as the non-homogeneous term. And also in particular, we're going to have a linear ODE that starts from 0 initial conditions. So take a look at this. So we're going to have a y double prime plus by prime plus cy equals delta of t. And in addition to that, we're going to have the initial conditions both 0. So both y of 0 and y prime of 0 will be 0. So once again, if you remember from the table, delta of t minus a is the delta function, or the unit impulse function at time a. Now this time can be 0, so that impulse can happen at time 0. So if a is 0, then of course this becomes delta of t. And you have actually a separate formula in the table for the Laplace of delta of t, simply because it's a particular case of this, but it has its own importance, right? I mean, if the constant is 0, the Laplace of delta of t is going to be just 1, because e to the 0 is 1. So if we start with initial conditions equal to 0, notice what happens if we take the Laplace operator on both sides, right? Because that's the first thing to do when we try to solve the equation. So we're going to have a L of y double prime plus b L of little y prime plus c L of y. And as I mentioned before, L of delta t, because a 0 is just e to the 0 times s, which is just 1. So L of delta t is 1. Now, when we apply the formula for the Laplace of y double prime, here we're going to get s squared big Y minus s times 0 minus 0, right? Because the initial conditions are 0. Here we have b s times big Y, again minus y of 0, which is 0. And this is c times big Y. So because, and it's important here to understand, because we started with 0 initial conditions, if you look carefully on the left side, you basically end up with the characteristic polynomial times y. So if you pull out y from all of these terms, you end up with the characteristic polynomial in S. So for this particular ODE, when you have 0 initial conditions, impulse unit function at time 0 on the right, then the Laplace transform of the solution has a very nice standard way. You basically could start with it if you remember, right? I mean, if you remember that you always end up with this, you might as well start solving the problem with this format, 1 over as squared plus bs plus c. Because everybody uses the characteristic equation so often in many other situations, this type of equation calls for a nice standardization. I just want to emphasize there's nothing special about the equation itself, except the fact that you have this nice format of the Laplace transform of the solution. And so that happens provided two things. The non-homogeneous term is the unit impulse function, and the initial condition are all 0. So, and obviously the solution I didn't specify A, B, C. We're going to go over examples next time. Obviously, the solution of the ODE will be the inverse Laplace of 1 over AS squared plus BS plus C. So because of this special format of the solution, and because when you use convolution, this particular format will appear as part of solving other differential equations using the convolutions, you will typically have special notations for this equation and for these solutions. So to use the notation in the textbook, this big Y, I mean this, let's actually write it here, this 1 over AS squared plus BS plus C. So this format is called the transfer function. And it's denoted typically by H of S, big H of S. I mean in our book at least. And the inverse Laplace of this, so I mean the actual solution of the ODE, is called the impulse response. And is denoted by little h of t. Again, to keep the convention that little h of t is the inverse of big H of S, right? The same convention of notation that the Laplace transform is denoted by a capital letter. So instead of big Y or little y, this is denoted by big H and this little h, at least in our book. The transfer function is also kind of a technical term. You'll see that it's basically like an intermediate step in solving a standard with convolutions, a larger class of differential equations, as you'll see later. The impulse response, you may guess why it's called this way, because delta of t is the forcing term, is the non-homogeneous term, and it happens to be the impulse function, and therefore the solution of the ODE, it's in response to that forcing term, so therefore it's called the impulse response. Again, typically in engineering applications, if you want, this right-hand side sometimes denotes a force. That's why it's called a forcing term. Doesn't have to be a force, but you know, if you think about the mass spring system as a typical example, that'll be a force, external force, and therefore the forcing term will be the solution in response to that forcing term. So that's the impulse response h of t. So before we move on to the next part of the lecture, again, let's review briefly what we accomplished so far with the convolution. So an operation which has this property, make sure you know how to use it, right? I mean, typically, you will see later, you will use it in reverse. When you take the inverse Laplace of a product of functions in S, you can write your inverse Laplace via convolutions, like this. And here's a couple of examples. And then remember this particular linear ODE that starts from 0 initial conditions and has the impulse function on the right hand side. It has the solution in a very specific form, namely the transfer function. I mean the Laplace of the solution is 1 over the characteristic polynomial, and then the inverse of that is called the impulse response, which is the solution of this ODE. So what we do in the next part is essentially try to solve the general linear ODE when the right-hand side is just any function, not just delta of t. And let's see how that looks like if at some point at the end I'm going to use convolution in writing the solution. So stay tuned for the third part.